Good morning, one and all. Today we will discuss the important topic of signals system, that is analogy between vectors and the signals. Now, in that the first one, as generally we will take the comparison between the vectors and the signals. The vector can be defined, will consist of magnitude as well as direction, and the component of vector v1 along with the v2 is being given by the c12 into v2. That is, the vector will be drawn like this. The component will be taken from the v1 with the v2. Can be obtained by taking the perpendicular from the end of the v1 to the vector v2. That is, v1 is equal to c12 into v2 plus va. This particular ve is nothing but the error vector, and the component that we have drawn will be a perpendicular here. Therefore, the component is the c12 into v2 and the ve is the error vector. And this is the one of the choice of drawing the component from the v1 to the v2. Hence, we'll use another one, that is another two more choices of drawing the component from the v1 to the v2 will be given like this. That is, v1 is equal to c1 v2 plus ve1, and v1 is equal to c2 v2 plus ve2. The first one will be drawn like this. That is, from the end of the v1 it will be drawn upon to the v2 like c1 v2 on the v2. Similarly, v2 is equal to c2 v2 plus ve2. That is, the component will be drawn like c2 v2 like that. Similarly, the concept of this orthogonality will also be extended. The concept of these vectors will also be extended to the signals, where the concept will be extended to the signals by the process of approximation. That is, we'll use the two functions f1 of t and f2 of t. That is, we'll approximate the f1 of t in terms of f2 of t as f1 of t is equal to c12 into f2 of t plus fe of t. f1 of t is equal to c12 into f2 of t plus fe of t. This fe of t is nothing but our error function, which is equal to f1 of t minus c12 into f2 of t. The one possible way of minimizing the error is integrating over the interval t1 to t2. That is, by taking the 1 by t2 minus t1 integral of t1 to t2, fe of t dt is dt. This fe of t will be given by f1 of t minus c12 into f2 of t dt. Right? But this particular error function will not be the perfect approximation process. Hence, why? Because we have the positive values and the negative values will be as it is been present. Therefore, the error will be more. To increase that, solve that particular one, we will use the next one, that is by squaring the error function. As it is been squared, therefore, correspondingly, the negative values will also be squared. It will become the positive. Then the positive values will also be there. These positive and the negative values combinedly will produce a sufficient error will be present in our approximation process. In the previous case, as the positive and the negative values, both of them will get cancelled, hence that indicate the error is 0. That is, I will say, false prediction. Hence, we are using the squaring of the error function. This squaring of the error function fe square of t dt will be taken. Our error function will be equal to 1 by t2 minus t1 integral of t1 to t2 fe square of t dt. This fe square of t dt will be written as f1 of t minus c12 into f2 of t whole square dt. This where e is the mean square error value of the error, the value of the c12 which minimizes the error, where you need to calculate the de by dc12 which equal to the 0. That is, while calculating any function to be minimum at a particular point, we need to take the derivative and equal to 0. That is, d by dc12 and making the e value has been 0. They taking the e value and making them into the 0. That's generally this e will be consisting of the two functions. One is the f1 of t, another one is the c12 into f2 of t. That taking their whole square, that is nothing but the a minus b whole square. Therefore, the first term will be the a square term, second term will be the minus 2ab term, and the third term is the b square. The first term indicates the f1 square of t, second term is 2 into f1 of t, c12 into f2 of t, and the third is f2 square of t and the c12 square. These are the three terms which is equal to 0. When solving this particular one, we will get the expression as the two terms of minus 2 c12 will get to minus 2 into f1 of t, f2 of t, and the c12 square will be split as the 2 c12 f2 square of t dt, and this particular c12 will be given by integral of t1 to t2 f1 of t f2 of t dt by the integral of t1 to t2 f2 square of t dt. This is the expression for our component, that is c12, while approximating the function f1 of t and with respect to the f2 of t. This is the main important, which is similar to that of the vectors, that is the c12 is equal to v1 dot v2 by v2 square. There in the vectors we will have the dot product, but in the signals we will have the integration. That is integration of the two functions by the integration of the second function will use the c12 component. Next, for checking the orthogonality, that is the two signals as 90 degrees, that is the phase angle between the two signals as 90 degrees, then the two signals is said to be orthogonal signal. For that the component is the c12 is equal to 0. When we substitute the c12 as 0 in the final above expression, then the denominator term will be gone, therefore the numerator term will be equal to 0. That is nothing but f integral of t1 to t2 f1 of t f2 of t dt is equal to 0. This is the expression. This is the condition for the two functions is said to be orthogonal. For example, the orthogonal functions are nothing but cos, if you take the one as the cos function and the other as sine function. If you integrate those two functions, then automatically it will be equal to 0, right? That is the case. That is the orthogonality condition. Similarly, the orthogonality condition will be present for the n number of functions. If you take an n number of functions like x1 of t, x2 of t, x3 of t, if to set these functions as being orthogonal, to say these all functions are being orthogonal, that is the first condition is that we are for illustration purpose we are considering the two functions as xj of t and the second one is xk of t. To satisfy this orthogonality condition, the first one is integral of t1 to t2 xj of t and xk of t equal to 0, where the j not equal to k. This is the case. Okay. Next, and let that t1 to t2 xk square of t dt equal to k, which is nothing but when the both the functions, that is j is equal to k, then the both the functions will be the same. Then integral of the t1 to t2 xk of t and xk of t, that is xk square of t, which will use a particular constant as k. When the both the functions are being equal, we will get a particular constant. When the both the functions are being different, then the two functions will be said to be as an orthogonal, which is equal to, their integration will be equal to the 0. Next one is, let the function which can be approximated with the orthogonal signal space by adding. Initially we have taken only one function, therefore we have taken only one component. Now we are considering the n number of components. Now these n number of components will be approximated in our process. Therefore the f of t will be represented with the number of components like this as c1 x1 of t, that is first component first function, c2 x2 of t, first second component second function, plus and so on cn xn of t, plus if there is any error, that function will also be represented, that is fe of t, and the summation of these all will be the summation r is equal to 1 to n cr into xr of t will be written, plus fe of t. Therefore the fe of t will be getting like this, fe of t is equal to f of t minus this particular summation. That summation will vary from r is equal to 1 to n cr into xr of t, like that. And the mean square error, generally the last expression what we have seen is nothing but our mean square error, which is nothing but the 1 by t2 minus t1 integral of t1 to t2 fe square of t dt, that is the mean square error. And 1 by t2 minus t1, that integral of t1 to t2, take the fe of t is nothing but f1 of t minus summation r is equal to 1 to n cr into xr of t whole square dt, right? The same expression for the n number of functions we have considered and substituted in our error function fe of t. Now this component which minimizes we need to find out the component which minimizes the mean square error. The mean square error should be minimum. For that, what is to be the component that we need to calculate. For illustrate, for getting that particular component which minimizes the mean square error, we need to differentiate that error function e with respect to the each of the components, that is C1, C2, C3 and so on Ck. That is dE by dC1, dE by dC2 and so on dE by dCk will be equal to 0, right? In general, these are the k number of functions. That's why we are considering one particular one, that is dE by dCk equal to 0. That is d by dCk, substituting the e value and perform the integrations, and all the terms that do not contain the c has been 0, and the summation when the r is equal to k term remains and all other terms will be the zeros. Therefore, when solving this particular entire expression, then integral of t1 to t2, that is minus 2 into f of t xk of t dt plus 2 into ck integral of t1 to t2 x square xk square of t dt equal to 0. And therefore, the ck will be equal to the integral of t1 to t2 f1 of t xk of t dt. Again, the integral of xk square of t dt. This is the C12 component. This is similar to that of the two function components only. That there the C12 is equal to integral of t1 to t2 f1 of t f2 of t dt and integral of t1 to t2 f2 square of t dt, like that. But this particular denominator function can also be equated to the to a particular constant of kk. When we substitute the denominator as kk, then the numerator will be given by the integral of t1 to t2 f1 of t xk of t, which is dt, which is equal to ck into hkk. Then that is the expression for the corresponding component ck. Next, we will calculate the mean square error. The mean square error generalized formula is same. The average of the mean square of f of t will be given by the mean square error, and it is denoted by the e is equal to 1 by t2 minus t1 integral of t1 to t2 f square of t dt, which is further be illustrated with these steps, that again we are squaring the corresponding one and getting the three parts like a square, b square minus 2ab, and as we know that the standard formulas for the CR square into integral of t1 to t2 xr square of t dt will be equal to the same CR square into kr, and the CR into integral of t1 to t2 xr of t dt f of t dt will be equal to the CR square into kr. Therefore, substituting these formulas in the above equations, therefore we will get the finalized expressions which is similar to that of the e is equal to 1 by t2 minus t1 t1 to t2 f square of t dt plus c1 square k1 plus c2 square k2 plus and so on cn square kn, like that. This is, if we have a one component, it is c1 square into k1. If we have two components, it is c2 square into k2. If we have n number of components, cn square into kn. That is the one, right? As the number of components will be increased, the error will be the less, right? That is the number of components, that means the approximation level will be increases, hence will get the error as very less. That is the main intention of implementing the n number of functions. If we do it for the only one function, we cannot get the error as minimum. That's why we are taking n number of functions, taking their components and calculating the mean square error, which will use the error as minimum. We can take it by the examples, like we can take it by the simple examples of calculating the mean square error with the n number of functions. Next, the closed order complete set of orthogonal functions. In the closed order complete set of orthogonal functions, now we have a set of n number of mutual functions. That is x1 of t, x2 of t and so on xn of t are the mutually orthogonal functions over the interval t1 to t2. These are the n number of functions. Now we are considering one more function of f of t, which is also orthogonal to each of the n number of functions. That is integral of f1 of t, h2 of t, When we integrate, if we get 0, then f1 of t, x1 of t is orthogonal. Similarly, f of t, x2 of t. If we integrate those two functions, again if you get 0, then it is said to be orthogonal. Like this for n number of functions. Then the f of t is said to be included in this orthogonal set. Then the f of t and these n number of functions will be called as the closed or the complete set of orthogonal functions. Okay? That is, f of t will be compared with the, or will be taken integration with each of the n number of functions. That's why we have kept it here the k. The k runs from the 1 to n. For the n number of functions, these integrations will have to be calculated and equal to 0. That is the thing. And if that f0 is said to be the orthogonal to each and every function of the orthogonal set, then this set is being the incomplete without f of t, and it becomes the closed or the complete set when the f of t is being included. Whenever the f of t is included, it is called as a closed or complete set of orthogonality. Without f of t, it is not a complete set of orthogonal functions, right? The complete functions of orthogonal functions. Next one has that f of t can be given with the n number of functions. Then the functions will be like this. These, for example, if we does not get the minimum error by using this n number of functions, therefore we need to increase this n number of functions to the infinity. If we increase the functions to the infinity, then we will get the corresponding f of t as being, f of t will be approximated effectively where it will minimizes the error. Okay, then the final one is the orthogonality in complex functions. In the orthogonality in the complex function, this is the case when the two functions are being complex functions. That is, f1 of t can be expressed in terms of f2 of t, and f1 of t and f2 of t are the two complex functions. f1 of t can be expressed in terms of f2 of t as f1 of t is equal to c1 to into f2 of t, like the previous one, neglecting the corresponding error, where the c12 is equal to integral of t1 to t to f1 of t, f2 square, f2 star of t dt, and integral of t1 to t to f2 square of t dt, right? Where this complexity term, that is the complex conjugate of the second function is included, then f1 of will be said to be for, that is the component will be calculated for the complex functions. That is c12 is equal to t1 to t2 f1 of t, f2 star of t dt, and the denominator same f1 of t, f2 square of t dt will be calculated. And if, for example, if these two functions are being orthogonal, then the c12 will be 0. Therefore, the denominator term will be gone. Therefore, it will be equal to the numerator term. And that numerator term will be nothing but our t1 integral of t1 to t2 f1 of t, f2 star of t dt equal to 0. And the above equation represents the orthogonality condition in the complex functions. If it is normal functions, similarly f1 of t, f2 of t. If it is complex functions, f1 of t and f2 star of t dt, like that. Next, these are the topics which will be present related to the approximation of the signals with the one function with the another function, one function with the n number of functions, and calculating the mean square error and the closed or complete set of orthogonality and orthogonality in complex functions. Thank you.